middle ones are a little hard. So you have middle board is a little hard to pull up and down.
Okay, so just leave it with application?
Well,
Both hands, it can be done with both hands.
Both hands, yeah. But it may, if you want to use only one, then it may be better to use the top one, right?
Yeah.
Okay, that is more.
So once you have to work, you have to work at least once.
Once, yeah. Okay, I think we can start. So we are happy to have Nathan Berkowitz, and he will talk to us about pure spinors.
Okay, so thank you. I think this is the third time I've been here.
Yeah.
So it's a pleasure to be back. So I've heard that people ask lots of questions, so that's the idea. I mean, I think I have the excuse of jet lag, so I can't answer a question. I still have 3 more lectures to think about it. So, so you can ask many questions, and I was told to go slowly, and that will depend on the question. So let me give a little motivation, and then I will give an outline of the things. If I can talk about them, if people want me to talk about other things, just tell me, and again, I have a few days to prepare, so but tell me today, not the last day that you want me to talk about something. So the motivation is we want, of course, to understand the superstring. So we have R and S. So if you want me to write bigger, tell me. So we have different sectors of the superstring. So this is, of course, I'm just going to talk about perturbative string theory here, but of course the idea is that you understand perturbative string theory well, it will help you to understand non-perturbative string theory. So we have different sectors of the string. So we have the Green-Schwarz sector and the Ramon sector. So of course I don't have to be using the RNS formalism to say what I mean by Green-Schwarz and Ramon. I just mean the bosonic states, which can be either GSO plus or GSO minus. So, in some sense, GSO plus and GSO minus are natural to talk about the RNS string. It just tells you in the Green-Schwarz sector if they have half integer or integer mass. So for example, well, maybe that's not the right way to say it, but the GSO minus sector are the ones which are not preserved if you have space-time supersymmetry. So for example, the tachyon sits here, whereas here would sit the gluon. In the Green-Schwarz formalism, they both appear essentially in the same way. So tachyon vertex operator is just e to the I k dot x times, let's say, k dot psi. Whereas the gluon vertex operator would be something like, using this notation, so it would be dx plus k. So everything is built out of these x's and psi's. And of course you can put in the goals, so I'm not going to go into that here, but essentially all of these vertex operators in the Green-Schwarz sector you can write down in a simple way. And you can even make n equals 1 worldsheet supersymmetry manifest if you want. So this one can be written as so kappa, let me call it different. Okay. I write down a superfield, capital X, and if I integrate out kappa, I just get this vertex operator for the tachyon. And if I want to do the gluon, I just do Okay, so if you write this out in components and integrate over kappa, you just get the same vertex operator here. Okay, where in this case the k dot psi always comes from this k dot x here, and this extra psi will come from expanding dxn. Okay, d is just dd kappa plus kappa dd. Okay, so that's the Green-Schwarz sector using the RNS formalism. It's RNS because we have n equals 1 Roche supersymmetry. We're doing open string, we're doing closed string, n equals 1 cohomology. Now, if we want to describe the Ramon state in RNS, life is more complicated. So we have to involve the ghosts. And Dan Martinek-Schenker showed us that we have to actually bosonize the ghosts. So this is Bethe and gamma, the ghosts coming from the n equals 1 superconformal invariant. And these are the free fermions and the chiral boson, which comes from, fermionizing these ghosts. So just to understand, since nobody's asked a question yet, how many people have seen this? Even better, how many people have not seen this? Okay, so everybody has seen, okay, maybe just a few people haven't seen this bosonization.
So Narayan did it last week.
Okay, let me ask you a different question. How many people did not see it before Narayan? Okay, so the Ramon states involve these fields, and even more complicated versions, you have to take the square roots of these exponentials. So the Ramon fermion, if I try to write it down, which would be something like the vertex operator for the gluino, using this language would be something like e to the minus phi over 2 times, where this phi is the same phi here, times some spin field constructed out of the psi's. Right, and might do something like sigma alpha, where sigma alpha comes from bosonizing the psi. So you like psi m fermionizing, bosonizing. So you write this is. And then the sigma alpha is something like e to the I over 2, sigma 1, with plus and minus signs here depending on the spinor direction. So this is called the spin field, and the 32 components coming from the 5 possible plus or minus signs here. So A is 1 to 5, so you choose 5 complex combinations of the psi's. So that breaks SO10 down to U. Well, if we Wick rotate to SO10, the choice of how we choose 5 sigmas here is related to a choice of how we choose a U5 subgroup of SO10. Okay, so only U5, or more precise, U5, a U5 subgroup of SO10 is manifest in this notation. U5 will reappear later, which is why I'm spending a few minutes saying what it is here. And now there are different choices. So it turns out this has 32 components, because we have 2 to the 5 choices here. But actually, under Lorentz transformations, you can show that they split up into 2 16-component representations, which are, of course, the chiral and anti-chiral representations of spinors in SO10. So if I choose plus an even number of plus signs, so for example, this one, so this has, of course, 2 pluses, or I could also have 4 pluses. Or I could have, of course, 0 pluses. So these transform into each other under Lorentz transformations, and of course there are 16 possible choices here, and you can, of course, have an odd. You could have 1 plus, or you could have 3 plus, So you see these break up under U5 into a 1. There are 10 of these, right? Because there are 10 different ways to choose 2 out of 5. And there are 5 of these. So I guess probably we'll call this one a 5 bar of U5. This would be a 10. This would be. And similarly, these split up into a 1, a 10 bar, and a 5. Okay, so this is one split up. This is a split up of an SO16 chiral spinor under U5, and this is how an SO10 chiral spinor, how it splits up in U5, and this is how an SO10 anti-chiral spinor splits up under U5. Okay, so in any case, this gluino is, let's call it, if it's in the GSO plus sector, this has to be chiral, which means it came from this one, let's say, this is chiral. Let's call this one anti-chiral. Okay, and if you chose an anti-chiral, so you chose an even number, an odd number with plus sign. Now this would not be a gluino, this would be something which is not supersymmetric. So this is GSO minus, GSO plus. So you can see that in the RNS sector, these two are more complicated than this. I don't know how to write these vertex operators in a way which makes the n equals 1 go, which is the supersymmetry manifest. And furthermore, I have to do all this Bosanization. I don't know how to write it directly in terms of the fields that appear in the original RNS act. Now, because of these complications, I know how to describe the RNS, using the RNS description, I know how to describe a superstring in backgrounds where I turn these fields on. So it's easy for me to describe RNS in tachyonic backgrounds, it's easy for me to describe RNS in gluon, or of course when I'm doing closed string in gravitational backgrounds. I essentially just add this to the action, and I get the RNS in these backgrounds. On the other hand, if I try to describe the RNS string in Ramon backgrounds, or if I'm doing the closed string in Ramon backgrounds, I don't know how to do it. Not only I don't know how to do it, I don't think anybody knows how to do it. Just because you have to figure out what you mean by this Bosanization in a curved background. And there are all these other issues that start to come in which have to do with picture changing. Probably it's not worth discussing here, but I'm not saying it's impossible to do. And certainly people have tried. But I don't think anybody has succeeded. So maybe this is a good time to stop for questions. Just because maybe some people think there is a way to do Ramon backgrounds with RNS. Does anybody want to say anything about that? Okay, this is a good audience to say this because probably people here have thought about it. So that's why I'm hesitant. I say you can't do it. Okay, so this is a problem with RNS. Of course, if we want to do ADS-CFT, we have to do Ramon background. It's also a problem if you want to do non-perturbative string theory, because non-perturbative string theory, of course, the Ramon fields mixes in a very simple way with the Nevers-Schwarz fields under the non-perturbative duality. So if you want to describe M theory, I think probably RNS is not the way to do it. And I think maybe there was one paper on trying to do with RNS, but I don't think it was used by anybody. So in any case, I don't know how to, one needs to go to a different formalism, and Green-Schwarz is of course the natural thing to try. So in Green-Schwarz, one has of course the same sectors of the string, but in this case, the fields which are easy to describe are not the gluon and the tachyon, it's the gluon and the gluino. So the starting point in Green-Schwarz is you have x's and thetas instead of x's and psi's. So of course m here I should have say m goes from 0 to 9. And alpha of course goes from 1 to 16. And the notation I will use, which is not, I don't think it's universal, but I think Witten also uses this notation, so in that sense it's universal. So he doesn't write spinors as 32 components, he writes them as 16 components, where an up index is if it's chiral and a down index is anti-chiral. So that's convenient because you can contract chiral and anti-chiral 10-dimensional spinor to get a scalar. Whereas you can't contract a chiral and a chiral spinor to get a scalar. So this already has more information than if you had everything with an up index. Okay, so the gluon, you can write, well, heuristically let me write it as dx and dk dot x. We'll find out later this is not quite right, but I'm not going to go into. Carlos will say something about the gluon vortex operator later, but I will also say, but you have some theta dependence also, but it's not so complicated. The gluino is of course a spinor, but now you can construct a spinor using theta. So
Nathan,
yes.
the previous question. I mean, if you take this Ramon backgrounds, I mean, there is this where, I mean, if you have a sigma model and you turn on backgrounds and beta functions vanishing as the equations of motion. So analog of that has not been done for the Ramon backgrounds.
Okay, so let me give an answer which may be wrong, but let me try to answer the question and then we'll see. So what you need to define the beta function. So normally you start with the matrix system. So let's start with the sigma model. So the sigma model is dx e bar x. Okay, then we have our psi. And normally one says that's the sigma model. Normally we don't put ghosts into the sigma model. So if we just start with this, then normally we say, okay, so let's just add the vertex operator. And we can ask if it preserves conformal invariant. So normally one says, okay, so the vertex operator, if it depends on x and psi, I can just compute the beta function and see if it's conformal invariant or not. At this point, we can't just yet do Ramon backgrounds because we need the ghosts. So now already, okay, so you can put ghosts in here, but what does it mean? Because now, normally the ghosts come from fixing conformal invariance. So you're not really supposed to put in the ghosts. So maybe this is I'm saying wrong. I'm not 100% sure, but I mean, do you want to put the ghosts in already here? And then now you do something like this. So there's some kind of enlarged sigma model or something like this. We could start to do something like that. Then there are other questions which come in, which are, this is just with one vertex operator. So at the linearized level, I think this is fine. But now you could start having back reactions of the V's with the V's. And now we run into a second order question, which is picture changing. So these V's, I mean, they carry a picture. So if people don't know what picture is, sorry, you have to learn it. Friedland Martin Schenker. So that means when you take the back reaction, so there's of course a 3-point amplitude, which is if you take a gluino, multiply it by Guino, you know you're supposed to get the gluon out. Why? Because this 3-point coupling is non-zero. That's just the usual psi a slash, sorry, psi area, is going to use a different letter. So if chi is the Guino field, then this is just the usual cubic Yang-Mills coupling, super Yang-Mills coupling. So that means there has to be a 3-point coupling between two gluinos and a gluon. But if you multiply this vertex operator by itself, you don't get this vertex operator here, this one here. You get something with picture e to the minus 5. So you have to hit it with a picture changing operator, which means the back reaction from this is not going to be cancelled by adding a gluon vertex operator, unless you put it in the -1 picture. You put in the -1 picture, then okay, then you have to put -2 picture, etc., etc. So there's some more fiddling you have to do. And again, I have thought about it a little bit. Some other people probably have thought about it more, but that I think those are the two big headaches. Is that somehow the ghosts come in to the vertex operator, which I think is I've never seen signal models on that, right? And the second is that you have this picture problem. I don't think people have solved. So I don't know if anybody has any comments. I don't know if Ashok, you want to add anything?
No, I think it's true that if you try to formulate a regular sigma model, it's not possible. I mean, the closest I can imagine happening is that in the context of string field theory, you may be able to define a modified VRST charge to squares to 0, acting on the Hilbert space, but that's not the VRST charge of the sigma model.
Okay, so let me go back to this. So, okay, so in this language, here we have the gluino and the gluon. And I guess if I want to use the same notation, you see here, if I call the index on theta an opt index, then to be consistent, I should have called this GSO plus and this GSO minus. Because you see, this has a down index like that one. So just to make my notation consistent, I will say that it's antichiral, which is in the GSO plus. Okay, now if you want to describe the GSO minus sector in Green-Schwarz language,
in the RNS also you will change notation?
I'm sorry?
In the RNS also you will change notation?
No, what I'm doing is I'm calling this one GSO plus. I don't know what, if there's some conventional GSO plus with chiral or antichiral, but I want the down index to be GSO plus.
But you will still call it antichiral.
If there's some convention on that, I'm happy
No,
to
it's fine.
switch.
I just wanted to make sure that it's clear. Okay.
So theta is a chiral spin, and the vertex operator for the gluino is an antichiral. Okay, so if I want to do GSO minus, that turns out to be a mess. Now this has not been discussed by many people, but I think you've discussed it, right? Some people here have discussed GSO minus. Haven't you discussed it? Was it your student who discussed GSO minus in Green-Schwarz?
GSO minus in Green-Schwarz.
So there was a paper that I remember, people were doing light cone Green-Schwarz and writing down D grains. And they were discussing the BPS, the non-BPS D grains.
Yeah.
Okay. That's an interesting subject of the audience. Okay, so the way to do the GSO minus sector is the thetas are not going to be periodic. So I should have said something more about the spin field. One way to understand why this is involved in the Ramon vertex operator is that the Ramon vertex operator, you know, the psi is antiperiodic when you go around this object. That's what Ramon means, that you have a square root cut to psi. So that's why you have to do this bosonization in order to generate the square root cut. Now there's something similar in GSO minus sector in Green-Schwarz, and theta has a square root cut. So when you have a vertex operator GSO minus, then you know that if this is a function z, that near z theta goes like square root of z, or it goes like 1 over square root. So it either has square root zeros or poles. So if you want to write the vertex operator for this in Green-Schwarz language, you have to do something similar that you did here, but instead of bosonizing psi, you bosonize theta. So you have to write theta e to the plus or minus I sigma. Now you have 8 of these instead of, so it's called a different letter. Let's call it capital A. So capital A is 1 to 8. And now you have this vertex operator is going to be something like e to the 1/2. So these are not the same sigmas, of course. And then there'll be other things here. Okay, what are these other things? Well, it's probably going to have to do something to do with ghosts, etc., etc., and Green-Schwarz. Okay? So you see there's an analogous structure between Ramon states and RNS and GSO minus states in Green-Schwarz. So what happened?
Is side N or side A?
This here?
Yeah, side A or side N?
This is psi n, because it's a plus or minus.
Yeah, but your choice in terms of sigma A, right?
There are 5 of these sigmas here.
Yeah, that is.
And I've split m, so psi n for m equals 0 to 9, I've split it into e to the I sigma A and e to the minus I sigma A. So 5 of them are here, 5 of them are here.
5%.
And the same here, so this 8 of them with the plus sign and 8 with the minus sign. So just by looking at conformal weight, you know that there has to be something additional here, just like there's something additional here. So the way Friedan, Martin, and Schecker found this is they looked at the conformal weight of this and said it has 5/8. So you need something with 3/8. I'm putting words in there ahead, but I imagine that's how they found it. There has to be something similar here. And what has been done, so it's going to have to do with ghosts, but in Green-Schwarz, at least in the usual Green-Schwarz, there's no obvious answer for the ghosts. You can find this from pure spinors, it's a mess, but I don't want to do that right now. But what you can do is do this in light cone gauge. So in light cone gauge, you only have 8 thetas. When you only have 8 thetas, A is 1 to 4. And then it's much simpler, because then you just have V equals 1/2 plus or minus I sigma 1 up to 4. And it turns out when you compute the conformal weight of this, you just get 1/2. So in light cone gauge, of course, you don't have any ghost dependence. Just like in RNS, in light cone gauge, this thing would just have 4 sigmas and you'd be finished. Okay? So in fact, that's a nice way to find the light cone relation between RNS and Green-Schwarz. So in fact, this in light cone gauge is just theta. Okay? So in light cone gauge, you only have 4 of these. So choosing plus or minus and choosing an even number of plus signs, you're just going to get 8 on this side, which are just going to be defined as these thetas. So you'll get the relation between, I shouldn't have called them the same letter, let's call these 5s. You get the relation between the sigmas and these 5s. And if I'm not mistaken, this was first found by Whitten. So he found a relation between the sigmas and 5. Okay, so that was of course they both describe the same things, but they describe them in very different ways. And RNS is good for describing Schwarz states in Schwarz background, and Green-Schwarz is good for describing GSO plus states in GSO plus background. So if you want to describe Schwarz states in background, you shouldn't use Green-Schwarz. Okay? But what I want to describe are space-time supersymmetric theories, in which these types of states appear. Okay, so that's why we want to do Green-Schwarz. Some people want to do both, and that's a big challenge. So if you want to do states, Ramon's backgrounds with tachyons, do it alone, because I don't want to hear about it. Because you're going to get the messy things on both sides. There's no way to, I don't know any nice way to do it. Okay, so this is motivation. So of course, RNS 95%, maybe even more, do that, okay? Well, used to do that. I don't know, people don't really do perturbative string theory anymore, but the ones that do, most of them do this. Whereas here it's really an unexplored area. So people have tried, in light cone gauge I think it's more or less understood, but light cone gauge is not so useful. So if you want to do things covariantly, there are many things to attack. So I'll discuss some of the things here. And obviously I'll do it using this pure spinor approach. Now, maybe somebody will find some better way to do covariant Green-Schwarz, but I think up to now, I think it's fair to say it's the best way to do covariant Green-Schwarz. So when I say covariant Green-Schwarz, I don't mean start with the Green-Schwarz action and covariantize it. That's not what I mean. I mean constructive theory with x's and thetas, which is covariant. Okay, any questions?
What is the status of light cone string field theory for Green-Schwarz?
So there are, okay, so let's go first to RNS. I think it's at the same status as light cone RNS, but let's see if you agree with me.
In light cone RNS has this picture changing upward contact terms, etc., which probably has not been worked out completely.
So I would say Green-Schwarz is identical. So there are, so as I just told you, there's a field redefinition essentially from the psi's to the thetas. So light cone Green-Schwarz was actually when people, okay, so as you know, there was a epoch of light cone string field theory where everybody was doing light cone RNS in the maybe late 70s. So this was people like Kaku and Mandelstam and people like that. And he did light cone RNS. And then in the 80s, there were about, I don't know, maybe 10 people doing light cone Green-Schwarz. So Mandelstam was one of them, but of course Green and Schwarz and people like Brink and people like that. So you just have XM and let's call it theta. I need a letter for the light cone index. Let's call it J, I guess. And, oh, sorry. So if we do light cone gauge, I need another letter. Okay, I'll use capital A. I don't think I'll ever use it again like I did here. So A is 1 to 8, J is 1 to 8. And then, so in light cone gauge, let's see. There's a cubic interaction, so you have IQ5. So light cone gauge size, just 5 box 5. Now, I want to put an operator here, so let me try it. Okay, so let's. So light cone string field theory is you have diagrams of this type, where this is the light cone interaction point. And now the question is if you need to insert an operator here in order for Lorentz covariance. So in the 70s, Mandelstam showed that you needed an RNS to insert an operator here, which was essentially dxj psi j. So this is the, and you have to regularize it because this becomes singular near the interaction point. And this became the light cone version of the picture changing operator. Okay, so in the 80s, what he showed is that there's an analogous thing in Green-Schwarz. So actually, I think this was first shown by Green and Schwarz, that you needed an operator here for Lorentz covariance, which was, in their language, it was, I'm trying not to erase this because it will become useful later. So it was something like dx j. And then there's a choice. So in Green-Schwarz, when you work in light cone gauge, it's convenient to split the thetas up into 4 and 4 bar of U4. So I have to say a little bit about so this is going off track, but I'm happy to do this because as long as you don't, it's fine. That's what you want me to do, is that right?
Yeah, what do you want to go?
No, I'm not in a hurry, but what I'm trying to say is if I can answer a question, even if it goes off track, I will, unless you don't want me to.
Don't.
Okay, so so what I'm trying to say is I don't know how I'm going to connect this with the rest of my lectures, but since I know the answer about light cone Green-Schwarz, I can have it. So my advisor was Manchester, that's why there's not many people. So the point is that in Green-Schwarz you have 8 thetas. But a nice way, if you just build a superfield out of 8 thetas, you have 2 to the 8 components. That's too many. You want to do Yang-Mills, which only has 8 gluons and 8 gluinos. So what you do is you break, so this is SO8, you break it down to U4. And in fact, it's not so different from when we're breaking SO10 down to U5. So we're going to split the 8 thetas into, I'll even use, I'm running out of letters, but okay, let me call 8 tilde. So 8 tilde goes from 1 to 4. Why did I write this? The other one, if I use, you'll remember, sorry. Okay, so this A is 1 to 4. This is the light cone version of that. Okay, now the idea is that the physical superfields only depend on these. So if you have a superfield that depends on 4, well, it has a ground state. Let's call it, for obvious reasons, let's call it A plus. Then you have a state with a single theta. And then finally you have the term with what's called A minus, which depends on all 4 thetas. Okay, so these you can count. You have 8 fermions and 8 bosons. And this, of course, breaks the SO8 down to U4. So this is the gluon. So it breaks up into a 1, 6, and a 1. And the gluino splits up into a 4 and 4 bar. Now, if you do this, and you have your interaction point here, it turns out that in order to define what you mean by the interaction point, you have to define, it's a state which is not SO8 invariant. So another way to say it is when I, so the external states of the string, okay, I'll say it in different ways, which maybe ring a bell with people in different ways. Psi is going to have square root cuts at the ends of the strings and also at the interaction point. Let me try to say why. So you want theta to be regular everywhere. Okay? But there's a map from this diagram to the upper half plane, which is in the form rho equals So this map takes you from the upper half plane to this diagram. In this case, R just goes from 1 to 3. Now, when you do this map, anything with conformal weight 1/2 is going to get square root cuts whenever d rho dz is 0. So the field of conformal weight 1/2, like psi, goes to transforms like this. Which means if psi was regular in the upper half plane, it's going to be singular at these points. And vice versa. If psi was regular at these points, it would be singular in the upper half plane. Now, what we want is we want theta in Green-Schwarz to be regular in this diagram. So actually what I said before, psi meant theta. Theta is supposed to be, for example, have no square root cuts in this I don't know what you call it. I guess it's called the string frame. Which means theta will have square root cuts when you map this to the upper half plane. So theta when you map this to the upper plane, let's call this point Z1, Z2, Z3. Let's call this Y. Then you're going to have Z1 here, Z2 here, Y, and Z3. And your theta is going to have square root cuts here. Now, it can either have square root cuts or square root poles, and depending on the choice, that's going to tell you which state is going to be related to these points here. So, of course, at these points it's natural, because we know that the external states are supposed to be some glue on, some state of super-Yang-Mills. So the way the state of super-Yang-Mills is determined is telling you which thetas have square root cuts and which thetas have square root poles at these points. But we learned something else. There's also a state here. So that means when you do this diagram, you actually have to specify which state is here. So let's call this state, it's a Yang-Mills boson, let's call it J. So that's the direction of the Yang-Mills boson. So it's related to which thetas have square root cuts and which thetas have square root poles here. And then what
this is the intermediate state, is that?
I'm sorry?
This J corresponds to the intermediate state which is being produced?
It's not being produced, it's just, in order to draw the diagram, you need to specify a state here. Now the amplitude is of course Lorentz invariant, but it turns out the picture changing, you have to stick an operator here, which is going to contract with that state. So that's what Green-Schwarz called their vertex. So, let me try to say it another way, which might be. So I'm not saying it clearly. I may try to say it more clearly tomorrow. But the point is that you have to stick in an operator here. And that operator, the vector index on that operator is going to contract with this. So if I choose the operator, I can do it in different ways. I can either call this J and then I I sum over j here. This is the analog of this dx dot psi. That's the analog of this. The other way to do it is to fix a specific choice for the thetas. But that, I can do that obviously in a U4 covariant way by just saying all of these theta a's have square root cuts here. If I do that, so that's picking a specific direction, then the operator you need to include here is dx plus theta a theta b dx a b plus theta to the fourth dx minus. Where this plus a, b, and minus are precisely this 1, 6, and 1. So this is what Green-Schwarz does. They inserted this operator into the vertex. So this was in the mid-80s. This was their light cone string field. Okay, so you need to insert an operator. The right language, it's not so nice as in RNS where you just insert an SOA covariant object. Here, because of the square root cuts, you have to do something more complicated. But in fact, you can show that they're the same just using this triality. So, in some sense, any problem with RNS translates into a problem here. Vice versa. So this is, it caused some confusion in the 80s. People were asking if Green-Schwarz could, or in fact, the string field theory could describe as a cubic theory. So there was a paper by Greensight and Klinkham, if I remember correctly, which said, no, you can't because you know that the action has to be supersymmetric, which means it can't possibly be cubic because it has to be at least quartic. And then, I don't remember if it was Mandelstam or not, but somebody, I think it was probably him, that realized that that quartic term came because this has contact term divergences when two collide, so you need a quartic term to cancel it. And I think Ted is here, right? Yeah. Do you remember who? Then, I think it was Wheaton's student who showed that there were contact terms that needed for NSR string field theory.
Yeah, so it was for an RNS formalism.
Right, this was Chris Wendt, right?
Yeah.
So I think it was after Greensight Klingler. I don't remember the order. I may be confusing. I think they were independent, but I think Wendt came after. And then that led to this whole thing about, Witten's cubic string field theory needs to be corrected and things like that.
So, from the low energy effective theory, if you, in the space-time, if you fix the light cone gauge there,
Yes.
then is there any direct contact that has been made with the light cone string field theory, with that form of the effective field theory?
Sorry. So you're saying low energy effective action? Is that the question?
Yeah, low energy effective action, you can fix light cone gauge in space-time directly.
But how do you? There's some backgrounds which are not consistent with light cone gauge.
But if you take a background which is consistent with light cone gauge.
Okay, so you're asking how can you connect the two? Is that you're asking how you get
From light cone string field theory to...
I'm not sure if you're asking a question. So there is a question about how to get the beta function equations of motion, low energy equations of motion from light cone gauge. Is that what you're asking? Or are you asking something else? I'm not sure exactly what you're asking.
Like there is a standard exercise which is like starting from string field theory and reproducing the low energy effective field theory.
So normally you reproduce not low energy.
Bosonic case people have done that.
So you reproduce the linearized action and then you can ask for the, I'm not sure it's low energy. Normally the reason why you want to do string field theory is because you want to look at the massive states. So you don't want to do low energy.
But that's a...
I don't know how to do. Let's do bosonic just to make sure because I think I'm missing the question. In bosonic string field theory,
Yeah.
how do you relate that to the low energy action, which is something like R plus alpha prime?
Yeah, at the linearized level, people have done that, and I think
Yeah, linearized level, of course, you can do it, but
close string, yeah.
This one.
I ordered the other one with general arguments. The gauge invariances can be related and so on. But I don't
I'm
know
sorry, linearized, I understand how to get this term from linearized. you can get this term from linearize?
No.
So then why?
You have two non-linear directions, and I don't think there is a concrete derivation of one from the other. I mean, you only look at the symmetries, right?
Yeah, but whatever has been done for the bosonic case, covariant way, the corresponding thing has been done for dipole string theory.
But about not much has been done, right? Except for the fact that bosonic string gives the same S matrix as string theory and hence must give the same known as the effective action. There is a direct derivation of this from bosonic string theory. Now you can of course derive the S matrix and then from S matrix you can reconstruct this.
Yes,
Right?
but string field theory would not be the way to do that.
Yeah. You know, you can get a string field theory S matrix from string field theory, but you don't need string field theory.
Yeah, I just don't. I wouldn't use string field
Yeah.
theory, so that's why I thought there was some reason you wanted me to use string field theory. But okay, yeah.
Yeah, so probably the same will be true for light cone. Right? From light cone string field theory, you can reproduce the S matrix and
Yes.
then from there you can
Yes.
construct this.
At least the backgrounds that are consistent with the light cone gauge. So light cone Green-Schwarz has been done for some things. Of course, Green-Schwarz did many things with it. I mean, they showed that the 4.1 loop amplitude was finite, which was an amazing computation that generated all this. Well, then they found some anomaly cancellation, which I don't understand why the anomaly cancellation generated so much interest, but certainly for me the finite computation was more interest. Okay, but in any case, we're not going to do things in light cone gauge.
So this operators, they are in this ones which are inserted.
Yes.
Yeah. So they are in the realistic homology, they are physical steps or not?
No, so this is light cone gauge, so there's no BRST.
But they are physical steps or not?
These are inserted, these play the same role as this operator here in RNS. So they're inserted at the interaction points in order to get a Lorentz covariant theory. So the next place this appeared, again, this is going in an off tangent. So this disappeared after, in the mid-80s, this was a hot topic. Then it disappeared, and then reappeared when people started doing PP wave scattering. So I don't know when this was, maybe 98 or 90. So the idea was just to generalize what was done before, but now in a plane wave background. And surprisingly, they ran into the same problems. But okay, sometimes you forget what the problems are, and then you rediscover them. Okay, so okay, any other questions or comments? Okay.
So there are these hybrid versions, right? I mean, there's RNS and
Okay, so this is something that I worked a bit on. So before going to 10 dimensions, one can ask, so of course you can compactify this, and some versions of supersymmetry, maximal supersymmetry, as we'll see, is in some sense simpler than lower versions of supersymmetry, but the thing that's more difficult is that we don't know how to write off-shell actions. Actions where all of the supersymmetry is closed without using equating to motion. But one thing that you can try to do is look at compactification, would give you, for example, n equals 1, d equals 4, n equals 2, d equals 4 supersymmetry. And it turns out those are related to these RNS formalisms by a field definition. This is going a little bit too far off target, so I mean I could talk about that, but then
I just want to know what is like rough. I mean, is there a one loop partition function?
Good. So let me say what has been done, what hasn't been done. Okay. So in that case, it turns out the difficulty is that you have to introduce chiral bosons. So even in 4 dimensions, it turns out that the matter system you have is you have x's and thetas. So you have a Clubbial system, which is c hat equals 3 or c equals 9. You have x is n is just 0 to 3, and you have the n equals 1 d equals 4 theta. So you just have theta alpha theta bar alpha dot. Now alpha is 1 to 2. And in addition, you get chiral boson, which I call rho. Now, we know how to do path integrals over the x's and thetas. We don't really know how to do partition functions for chiral bosons. I mean, this turns out to be a chiral boson which has the same problems as the phi in RNS. It has e to the phi, e to the rho turns out to have negative conformal weight. So it's a time-like chiral boson. And if you try to compute, for example, tree amplitudes, everything works perfectly, and you get n equals 1, you get the amplitudes of the remote, you get the usual scattering amplitudes, but written in an n equals 1, d equals 4 manifested space-time supersymmetric manner. When you try to do loops, you have to struggle with this rho. So there's some things that were computed with loops that turn out, the amplitudes you compute turn out to be independent of rho. And those work out correctly. So, for example, these topological amplitudes, these ones that generate r squared, which probably Narayan talked about, r squared f, I think I'm right, 2g minus 2, is that easy? So these amplitudes you can compute very nicely in this, and in fact, it comes out in the manifestly n equals 2 equals 4 supersymmetric manner. But if you try to compute ones which are not topological, which involve more complicated dependence on the moduli, nobody's been able to do it. So that's essentially the status of, at least for loop amplitudes, that's the status. Okay, any other? So I haven't given up, but it's worth people looking at, trying, because normally if some things are more complicated, and there's no obvious reason why it shouldn't work, maybe it's worth looking at. But for example, Bianchi and collaborators have written some nice expressions for just the one loop, for different calabials, for getting the one loop amplitudes for 4-point amplitudes, and nobody's been able to derive it from this hybrid form, but I think in principle it should be possible. Okay, so now let's go to 10 dimensions. Okay, so just give just for people who maybe don't know if they want to stay for the whole time, let me give an outline of what I'm planning to do. But it's just planned, I'm happy to deviate or do anything else. So first is a superparticle. So the most interesting case is d equals 10 and also d equals 11. So d equals 11, we don't really know how to generalize it to something like the membrane, but the fact that it works nice for the particle makes us think that there might be some generalization. So this is, I mean, it's an open problem. There's been work on it, especially by Sidewall, but I think aside from Sidewall and his collaborators, there hasn't been much done in 11 dimensions. But then I'll do the string. Okay, so depending on, I'll see what Carlos is going to do, but I mean, obviously the thing you want to do is amplitudes. So it's not clear what Carlos will do, but what he doesn't do, I'll try to do. And then, of course, the next thing to do with the superstring is curved backgrounds. So I'll concentrate on ADS5 times S5. So again, some things have been done, but there are many open problems. So I think the idea of this thing is to tell you exactly where the open problems are. Okay, and then the last thing, which is, I guess, what I've been working on most recently, is the connection of twistors. So twistors turn out to be related to spinors. So these are the main topics. And if there's some specific subtopic you want me to think about, tell me as soon as possible so I have time to remember what was done. But, okay, so the starting point is a superparticle. So I have to tell you first, okay, so I think everybody knows, but I'll say it anyway. So the spinning particle is a particle which has spin 1/2 and describes a space-time fermion. So if you take the Ramon state of the superstring and just look at the zero modes, you get what's called the spinning particle. So that you can think of, at least in the Ramon sector, as the baby version of the superstring. But there's another thing you can do, which was started by Brink, I think Green-Schwarz, which is the particle, it's not a fermion in space-time, it's a super Yang-Mills multiplet in space-time. So it's supposed to describe not just the spin 1/2 state, but also the spin 1 state. So the way it was described, I think the simplest way to describe it is in first order form. So it's massless. You can do the massive version too, but I'll just do the massless version. So you start with the massless version for the this would be the massless version of the spin 0, and you supersymmetrize X. So supersymmetrize X means, so now I have to remember my conventions. So I'm going to try to copy conventions that Carlos uses, just because he's consistent and I'm inconsistent. But I'll try not to make mistake. So there's a question if you put an I here or not, or even a factor of the half. The half I will put. And normally you put an I here. But I like to avoid all I's just because it makes life more complicated. So I will not use I, and I think Carlos also you don't use an I, right? So let me say why you want to put an I and how you avoid it. So if you want this to be real, using the convention that Hermitian conjugation flips the theta with theta dot, you need to put an I. Because gamma M is a symmetric matrix. If you don't split the positions of these when you take Hermitian conjugation, then you don't need an I. Okay? So that's the convention I'm going to use. This is Hermitian in the sense that Hermitian conjugation, you don't flip the two positions. Okay, so in some sense, it's trivial to translate from one to the other. You just put the I back in all the formulas. Okay, so we want to quantize this. Now, how many people have never seen this before? Everybody has seen this before? Okay, so just a few have not. Okay. So I was told people don't know Green-Schwarz, but most people do that. Is that right? Okay, so you have constraints. So I don't know. Can I go over this quickly? Is easy? Okay. Okay. So you have constraints coming from the fact that the canonical momentum to theta is related to theta. So if you define the canonical momentum to be here with theta dot, then you find that it's related to theta, so you get this is equal to minus. I'm just worried about the signs. Yeah, I think this is the right sign. Okay, so that means dl this should be equal to 0. Okay. So this is the Green-Schwarz constraint. first and second class P's. So if you take the Poisson bracket of D alpha itself, and I use the convention that P alpha with theta beta is equal to delta alpha beta, then D alpha with D beta is equal to P n Okay, now I have to tell you about these gamma matrices. Carlos, are you going to do this today? Gamma matrices?
Yes.
Okay, so I'll leave it for Carlos. So these are symmetric 16 by 16 matrices. And this means that half of these constraints are first class and half are second class. So the way to see that is that if I take the square of this here, I get p squared. So gamma m, I think it's obvious. So I call this operator O alpha beta. Then it's easy to see that O alpha beta. I'm just worried. I can't take the square of it because it says 2 down indices. Okay, so I have to, what I can do is I can try to invert it. And you find that it's not invertible. So that means they're first class. But it's not invertible because p squared, naively you would say, well, the inverse is p slash without indices. Okay, I think I have to say something about gamma matrices or people will be lost. So 10 dimensions, normally one writes 32 by 32 matrices. But you can choose a Dirac representation which they split up in this way. So these are 16 by 16 matrices which take a chiral spinor, something with an up index, into an antichiral spinor, something with a down. Whereas this takes an antichiral spinor, the down index, into a chiral spinor. So this object here looks like the inverse of this. If you divide by p squared, then it looks like this is the inverse. But of course p squared equals 0, it's a constraint. So that means there's a first class piece of this. And you can show that the rank of this is exactly half of 16, so the rank is 8. Okay, so 8 of these 16 constraints are first class and 8 are second class. Okay, so I went over that fast and I'm happy to go into more detail if people want. So this is standard you can get from chapter 5 of Green-Schwarz with me. So one way to quantize is by choosing light cone gauge. So because half of these constraints are first class, it means there's gauge symmetries associated with this. And the gauge symmetries are called Kappa symmetry. So Kappa symmetry is generated by this object, P slash D. So this object turns out to be first class with itself. So of course, D equals 0 implies P slash D equals 0. D has part second class and part first class, and if you contract D with P slash, that essentially pulls out the first class piece. I mean, this is all first class. The easy way to see that is that you have to commutate this to itself. Now you get, instead of getting this, you get P cubed, so you get P squared times this. And this is 0, of course, using the first class constraint P squared equals 0. Okay, so these are the first class constraints. It looks like there's 16 of them, but actually it's reducible. Only 8 of them are independent. Okay, so how do they transform theta? Well, they transform theta in this way. So the parameter kappa so kappa is a spinor, anti-chiral spinor. It has a down index. In other words, if this is the generator, it transforms theta in this way, and it transforms theta x in this way. Okay, when you plug this into the action, you find its invariance goes up to a shift of E. You need to also transform E. E transforms as okay, so this is a symmetry generated by the first class part of G alpha. So kappa is the parameter of the symmetry transformation.
You just calculate the Poisson bracket of x and theta with this, and then get you.
That's right. That's right.
Yeah, I'm saying for getting the delta xm and delta theta, you just calculate the Poisson bracket.
That's right. So d alpha, because of the p in d alpha, that's going to generate this transformation of theta. And this term gets two contributions. One comes from this one here, but I guess that one, let's see. So the one that, that one vanishes because D is 0, right? Because it's this thing here. So but there's a contribution coming from D with X, and that's from the generator. Now to get this one, maybe you know, I don't know how to generate the transformation of Lagrange multiplier from Poisson brackets. You have to do field anti-fields.
Well, you have used the p square equal to 0. So in some sense you have used the equations of motion of E has already been used.
Yes.
So that's why you cannot just get it from Poisson bracket here.
Okay, but in any case it's easy. You plug this back in and you get this.
Theta is real.
Okay, so we're in 10 dimensions. So if we work in SO91, then the theta will be Majorana bar. Now I'm being flexible because I already said once I would rotate to SO10. If you work in SO10, theta can be via, but it can't be Majorana. So the thing you have to remember is that the complex conjugate, the complex conjugate of theta will never appear. So if I'm working SO91, there is no complex conjugate.
That's when the action there is a theta star in the S.
Okay, so that's right. In my notation, you never put bar, there's no theta star.
And gamma 0 is 1 in your basis. Right? So that's why
Gamma 0 is 1.
So thetas are just Majorana by S, that's the standard
Yes.
Majorana by S.
When we're working in SO91, yes.
But you have to use SO10 or you'll always work in SO91?
I will actually sometimes work in SO55, the simplest way to say it is I can always work in SO91. Okay, so to go to light cone gauge, we use this symmetry to gauge fix half of the thetas to 0. So you can gauge fix gamma plus theta to 0. So gamma plus has rank 8, so it kills 8 of the thetas. And in that gauge, the action simplifies. So the only part of the term theta dot p slash theta which contributes is the part where this is gamma minus. Now, in order to choose this gauge, I have to assume that P plus is non-zero. Because the transformation of gamma plus theta will be proportional to P plus. Now, if P plus is non-zero, I'm free to divide by it. So I can write this term as minus 1/2 C dot. There are 8 of these. So I'm just, let's call it 8. This term is equal to this, where CA defined as gamma plus theta divided by square root of P plus. Sorry, times. Get it back. Times. Kind of sorry. So now this has the form of a free fermion. So we know how to quantize this. So actually we don't need to go to complete light cone gauge. I guess for the particles it's just light cone gauge. So what we've done is we've assumed P plus is non-zero, we've gauge fixed away half of the thetas, and that simplifies the quadratic term to a term that we know how to quantize.
So you have one power of gamma minus in the definition of sin.
Sorry?
You have one power of gamma.
I have one.
No, you have gamma minus 1 power here, right? And the action is 1 power. How come the square? You have gamma minus here, right?
You're asking me.
When I square it, how do I get gamma minus here?
Okay, so you understand this term?
Yeah.
Okay, so I write. So this term is the same as this term here.
Which one? That should be.
Okay, so this is equal to. So maybe it's notation which is bad, but I'm writing this like this. Gamma plus.
This is IIT probably of that, right?
So gamma plus is something which only has non-zero components when both of these are A.
So, but it's off diagonal, right? And, or no? Or maybe
You're asking about gamma plus?
yeah.
Okay, so gamma plus is an 8 by 8 matrix.
Oh, okay. And this sits in the off diagonal element of
Yes.
the full gamma. Okay, yeah.
So there are 8 of these. Gamma minus is and what he was saying, the big gamma, the one with 32 by 32, I take plus something like 0.
I think this should be like then gamma minus and gamma plus gamma minus will vanish, right? And these problems is sitting in the off diagonal.
No, because they appear in different.
Oh.
I understand what you're saying, yes. Yeah, because, no, it doesn't vanish because this, so gamma plus can either have up indices or down indices. So these are when they're both up. When they're both down.
When you are writing it this way, it may be capital gamma minus, isn't it? I mean,
Sorry, let me say it my way and then we'll try to say it. Okay, so I have gamma plus with 2 down indices and gamma plus with 2 up indices.
Okay.
In my notation, this is 1, 0, 0, 0. This is 0, 0, 0, 1. Gamma minus, now we have gamma minus with 2 up indices. Gamma minus 2 up indices. I hope I'm doing this right. Gamma minus with 2 up indices is 0, 0, 0, 1. Gamma plus, gamma minus with 2 down indices is 1, 0, 0. So for example, gamma plus gamma minus, I have to either have these 2 down. So I think up to factors of 2 and things like that, I think that's. So I apologize, I mean, maybe it's unfamiliar, the notation.
Gamma minus, I think, is 1, 0, 0, 0 with upper indices.
You think it's 1 here?
Yeah, because if you multiply with gamma plus, you.
Yes, you're right.
Both the minus. Oh, same.
So
Yeah, that's it. Yeah, now it's right.
Okay, so now we got to this form. And now we can quantize. So the states are just I can do it in 2 different ways. I can either think of the states as being functions of xn, which transform as, I'll say what spinors mean in a second, but these are SO8 chiral spinors. So A equals 1 to 8. So SO8, I think people probably know, but maybe not. So it has 3 8-component representations. 3 representations with all of them have dimension 8. One is vector, one is chiral, one is anti-chiral. Let me say SO8. You have vector. It's called J equals 1 to 8. Chiral spinor. Capital A equals 1 to 8. And then you have anti-chiral. It's A dot. Call it A dot. And there are Pauli matrices associated with these, which has 1 index of each type. Now, normally you would think of fermion as being related to a gamma matrix of vector indices. So for example, in the INS string, this would be a psi j. And we know that the 0 mode of psi j generates, acts the same as a gamma matrix. In our case, we have C, which satisfies the gamma matrix relation. But now this is a chiral SO8 index, and not a vector SO8 index. Which means when you describe representations, the representations, if it was a vector index, would be spinorial. Since this is a spinorial index, it turns out the representations either have an A dot or a J. So then SO8 is an SO8 triality, which tells you that essentially you can do a rotation of these. I don't know the right mathematical way to say it, but you can treat any of these representations as the same as any of the others. So what that means is that because the the psi is a chiral spinor, it means the representations are either going to be an anti-chiral spinor, which are called chi dot, or a vector. So these I should think of as a spinorial representation, spinorial quote, of this object here. So how does CA act on this? Well, CA on phi A dot is equal to sigma. I should tell you, in SO8 you can raise and lower these indices using a delta. Okay, so if these are up or down, it doesn't matter for SO8. So I can write this as J A dot times phi j. So this is how psi acts on an anti-chiral spin, and it acts on a vector. And this way, sigma j A dot phi a. So that's how the psi operator acts on these states. And you can show that with this definition, this is satisfied. So these are the states you get in Green-Schwarz when you work in light cone gauge, which is, of course, the superannual states. Okay, any questions? Now, of course, they still have to satisfy p squared equals 0, because that's, if you use the usual Dirac procedure, p squared is the first class constraint, so all of these are on mass shell. Okay, this is a good place to stop, or should I? Okay, so when we come back, for people that come back, we'll see how to get this in a covariant way.
Take half an hour break.
Okay. Okay, so before I start, any questions?
Gamma plus minus are linear combination, gamma 0 and gamma 9?
Yes, so gamma 0. Okay, so I didn't say this. So gamma 0, adopting this. I think the usual choice is minus. And then gamma 9. I may have changed signs, but that's. And so gamma plus is this plus this. This. So you see it up to minus signs.
Gamma 0 square should be added.
I'm sorry?
Gamma 0 square should be added.
Okay, so am I using the plus? It depends, I'm using the plus, minus, 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 or the minus. So it looks like I'm using the condition where the 0 is minus 1.
Yeah, the upper index will get converted to lower index, right? So it will be minus 1.
Yeah, so I think I'm using convention where the only moment the minus sign is in the 0 direction. Okay, there was another question?
So, yeah, you said like this construction is for light cone gauge. Where is this used in this particular?
So I needed to choose this gauge here. So actually, people use light cone gauge in different ways. So if you do the string and you only choose this, it's called semi-light cone gauge. So I haven't chosen in strings. You know, you can choose tau equal to x plus because of reparameterization there. I haven't chosen this. I don't need to choose it. So people call this gauge semi-light cone gauge because I've just fixed the thetas but not x plus. Okay, any other questions? Okay, so now we want to do this covariantly. And one can ask why, and I think I already mentioned it. In light cone gauge, you have contact terms, and in general, you want as many symmetries to be manifest as possible. And although light cone gauge is not inconsistent, it turns out to be much more complicated than covariantly. And of course, if you want to do curved backgrounds, not all curved backgrounds deserve a possibility of choosing light cone gauge. Okay, so there are different ways to guess how to get the right answer. And one thing, obviously, you want to end on some covariant description of Super-Yang-Mills. So I'm not going to say too much about this because Carlos will discuss it this afternoon. But like Yang-Mills, ordinary Yang-Mills, you of course have a gauge field. But because you want to do Super-Yang-Mills, you know you have x's and thetas. So just like AM is associated with ddxm, there's a covariantization of ddxm, you can also covariantize dd theta. So one could associate a gauge field with dd theta also. And now if you want to do things in a supersymmetric way, they should be superfields, not just ordinary fields. So these are the gauge fields or gauge superfields of Super-Yang-Mills, which means they transform under gauge transformations in the following way. So delta A alpha equal B alpha, the gauge transformation, just like delta AM. So this is at linearized level. If you want to do the full non-abelian Super-Yang-Mills, then these D alpha and dm become the full covariant. So D alpha is kind of dd theta alpha. Now, I'll try to get the convention later in a second. So dm always means ddxm, and now the conventions. I think in my conventions is plus. Okay, so so you want to introduce these superfields, but it turns out this has, of course, too many components. So you have to impose equations of motion. It turns out at linearized level, the equations of motion can be written in the following way. So A alpha and AM are superfields, but they're not independent superfields. Now this, of course, implies that AM can be expressed in terms of A alpha and A beta, just you multiply both sides with MM, but it implies more. It implies that it turns out, this is of course a symmetric bi-spinor, and if you decompose it in terms of gamma matrices, it turns out in 10 dimensions you can have a 1 form or a 5 form. So this implies that the 5 form is 0. And of course the 1 form is just going to give you AM back. Okay, so this is a covariant description of Super-Yang-Mills. Nobody knows how to get this from an action principle, and that's not what I'm going to describe here, but at least the equations of motion, which tells you describe on-shell Super-Yang-Mills, are essentially these two equations. In fact, this is really all you need, because you can think of AM as just being an auxiliary field. It's not an independent field. Okay, now to get this equation from some kind of quantization,
This equation is true for every n1 and n2.
that's right, in any 5-point vector. the first thing we're going to do is we're going to construct some BRST or some operator which has the property that when you act on it on P, I'll define it this way. What you can show is that QV equals 0 and delta V is 2 lambda implies that V describes okay, so I have to tell you what this lambda alpha is. So D alpha, which I'll define here, satisfies the relation with anti-commute D alpha and D beta, you get gamma m alpha beta dm. So that means if lambda alpha, this is supposed to be understood as a fermionic operator. So lambda alpha should be bosonic. And if you want q squared equals 0, it's clear that lambda has to satisfy a constraint. I'm going to impose that lambda satisfies constraint. So this is called a pure spinor in 10 dimensions. So I'll tell you more about what pure spinor is, but let's just say this is the definition. And now one can use this property of D alpha to see that q squared equals 0.
This Q you wrote by guesswork. How did you get that Q?
I just wrote it down for now. I will tell you later why I wrote it down. But what I want to argue now is that if I define q in this way, and I define v in this way, that these two equations imply that v describes on-shell superannuals. So let me just show you that. So first of all, this is clearly a gauge transformation because q squared equals 0. So we've shown that q squared equals 0. Now let me show that this is the same gauge transformation as this. So q just acts like lambda alpha d alpha, and when I define v to be lambda alpha a alpha, then it's clear that this is the way a alpha transforms. Now finally we have to show that qv equals 0 implies this equation here. Okay, so qv is equal to lambda alpha d alpha lambda beta to beta. This is automatically symmetrized in alpha and beta because they both contract with lambda. So this is equal to lambda gamma m up to some parameter in front times gamma m alpha beta d alpha beta plus. So I just do a fierce decomposition line. So there's some coefficients here, I don't know. Something like 1/100 times, just some number, okay, that you get from the fierce decomposition. Now this term is 0 because of the constraint on lambda. So we see that qv equals 0 implies that this is 0. It has to be 0 for every lambda, so for every possible choice of m1 to m5, this has to vanish, which implies this equation here. So we see that with this choice of q and this choice of v, this describes on-shell superannuals. This was first shown by Paul Howe. So this was done in the early 90s. Okay, any questions?
So these works up to certain number of dimensions, I presume.
No. So this only works in 10 dimensions.
I see. So what goes wrong in 11, for example?
Okay, let's do well. What goes, first of all, there's no 11-dimensional superannuals, but we can do the exercise anyways. Okay.
One question, why is there no term with 3 gammas in the field?
That's antisymmetric.
Oh.
So in 10 dimensions, you only have one form. Okay, so let me do 11 and then we'll
And the 9 index is just related by epsilon, I guess.
say that again.
With 9 m's, that's related by epsilon. Is that the reason why I'm treating? Lambda, gamma, m1.
Yes, yes, yes. So the 9 form, you think? The 9 form is dual to the 1 form. So let's just count, just for an exercise. So if you have two spinors, so 16 times 16, and that has 256. So that splits up the symmetric part, let's say 16 times antisymmetric part of this, so that's 100, that's 120. And the symmetric part, I guess, is competition is 136. So the antisymmetric part is just a 3 form, so that's 10 times 9 times 8 over 6. And this one splits up into a 1 form, which is 10, plus a 5 form. Now the 5 form you might think is 10 times 9 times 8 times 7 times 6 over 5 factorial, but that's not right, because the 5 form in 10 dimensions can either be self-dual or anti-self-dual. And the gamma matrix, so that depends if the indices are down or indices are up. So it's only half of them, so that's the right answer. So that's the, this should give 126, so that's an exercise. Okay, so now I was asked to see what happens in 11. So, okay, so you can certainly define a pure spinor in any dimension. It turns out the naive definition of just setting lambda, gamma, lambda equals 0 as a pure spinor, that's incorrect, but we can do that in 11. So in 11, it turns out the gamma matrix is still, okay, it's symmetric, so let's see, let's go with, so this is actually going to come up later. So I call this a semi-pure spinor, just because in 11 dimensions, so this was 10 dimensions. In 11 dimensions, the symmetric spinors, the symmetric gamma matrices are 1 form, 2 form, and 5 form. So if you do the same algebra as I did before, so A is 1 to 32 now, and if you take the symmetric part of 32 to 32, you get either a 1 form, a 2 form, or 5 form. This is of course no longer self-dual because you have 11 indices, not 10. So there are actually 2 types of constrained spinors. Of course, if you constrain all of these to be 0, that tells you that lambda is 0. That's too strong. Okay? But you can either have this one, where you constrain both the 1 form and the 2 form to be 0. That's what most people would call a pure spinor in 11 dimensions. Or you just constrain this one to be 0. So that, I call it semi-pure spinor. Okay, so now one can ask, let's construct Q. For Q squared equals 0, of course semi-pure is enough, because this algebra is still the same. So D with D is going to be gamma M. So that's enough. Okay, now we can look at this and we can ask, so let's define D to be lambda A. And one can ask, what does QV equals 0? So QV equals 0 is going to imply that both the 2 forms, so we're going to put EAAB, gamma MN, AB, is equal to 0, and that this 5 form is equal to 0. show is that this implies that AM is equal to BA. Except, of course, when A is a constant. So what you find is that this vertex operator, in some sense what you're doing is computing the cohomology of this operator Q. It goes to number 1. And you find that the only cohomology is the zero mode cohomology.
So this is if you include both of these constraints.
Okay, yes. Now you're going to ask me what happens if you include. No, this is if you include just this constraint. Because remember, this constraint is the one that's.
On A there are two constraints.
Sorry?
On A there will be two constraints. If on
That's
lambda
right.
there will be
That's
one
right.
constant, then on A.
That's right. Now you might want to ask, suppose I have both constraints here. I don't know the answer. The answer is no, I just don't know the answer. But I know that it doesn't, well, what do you want? You want to get 11-dimensional supergravity. In order to get 11-dimensional supergravity, the answer, the way to get the right answer is to consider this vertex operator. So I'll call this B. Where this operator is the 3 form. So this is what we're going to do later. So maybe let me say that later. But there's another question that I can say now, which is suppose you do this in less than 10 dimensions. Suppose you don't have maximal supersymmetry.
So why this nomenclature only when we have two constants? It's called pure spinor and not.
So why is
Asking about the nomenclature, you said you add that other constant, gamma element constant.
Yeah, so what is meant by a pure spinor? So a pure spinor usually is the most, the spinor with the least amount of components, which is consistent with Lorentz symmetry. So in 10 dimensions, the only symmetric bispinors is a 1 form and a 5 form. So if I set the 1 form to 0, then I can't set the 5 form to 0 because that would set the whole thing to 0. But in 11 dimensions, you have both the 1 form and the 2 form which could send to 0. So it turns out if you just constrain this one, lambda has 23 components. A goes from 1 to 32, but this constraint turns out to kill 9 of the 32. It turns out if I also impose this, lambda has 16 components. So if you define a pure spinor as a spinor which is the minimal representation, then in 11 dimensions the natural definition would be this, which has 16 components. With this definition, I don't know how to get any interesting cohomology. I'm not saying there is no interest in cohomology, but I don't know how to get it. Whereas with this one, at least in ghost number 3, you get an interesting cohomology, which is just supergravity. Now, it wasn't obvious. So in fact, Paul Howe, in his paper where he discusses this, he discusses 11 dimensions also. But in fact, he uses both of these constraints. And he does. Okay, if you want, I can look at his paper and tell you in the next lecture what he did, but I don't remember what he did in 11 dimensions. He was discussing loop space for 11 dimensions or something like that, and I don't remember. But what I found and what was independently found by a group in Sweden, in Chalmers, was that this constraint, this cos number gives you 11-dimensional supergravity. Okay, if you go to lower dimensions, then it turns out that this is not strong enough. So let's do in 4 dimensions, just to see what happens. In 4 dimensions, a pure spinor is just a chiral spinor. So remember, alpha, so in 4 dimensions, a spinor can either have alpha or alpha dot indices. So a pure spinor is just a chiral spinor. That's the minimum representation you can choose. So the constraints are just lambda alpha d alpha. Now, if I call this Q, and I call V as lambda alpha A alpha, then this just tells me, this constraint here just tells me that d alpha A beta equals 0. That's not strong enough to give you equations of motion for n equals 1 superintegrals. Okay, the equation of motion for superintegrals is, you need this equation, but in addition to this, you need the equation of d bar squared A alpha equals 0. So that doesn't follow. So when you don't have maximal supersymmetry, you still can construct this operator, but it doesn't give you on-shell condition. Okay, only when it's maximally supersymmetric do you get on-shell condition.
Is there any way we can define V otherwise so that both are, you can see both?
So that you get this?
Is there any way to define a V with a operator such that we get both constants?
This one you mean both? You mean this one and this one? Okay, I could say something about this. So in the hybrid formalism, which was asked about earlier, I claimed you could describe n equals 1, d equals 4. In hybrid formalism, you have n equals 2 world-sheet supersymmetry, which means you have a Q and a B. So Q, we'll see B later, but B does have something like d bar squared in it. So there is a way to get this, but not from, at least, you would need to add another operator here, which would be something like d bar squared. Okay. So you can do it. It's not that you can't do it, it's just, it doesn't appear in such a simple form as in the maximally supersymmetric case. Okay, so let me go back to this. Okay, so where does this Q come from? So this is still. So normally I get Q, if I now interpret Q as a BRST operator, naively you would like to get some gauge fixing procedure. Now, if I have time at the end of the lectures, I can say one way to get this, in which you interpret lambda as a twistor variable. But at the moment, I want to get it in a much more naive way, which is just by taking this action and just adding a Lagrange multiplier times d alpha. So let's call the Lagrange multiplier f alpha times d alpha. So,
Sorry, what are you doing now? Adding this term?
we know the answer.
You want
The
to
answer is
get
this.
from action?
I want to get the answer now from some gauge fixing. No, this is a BRST. The answer, so for anybody who has studied BRST, this is BRST, right? You have Q and you define this as the cohomology, and if you were doing bosonic string theory, Q would be something like C times T. If you're doing, but we're doing the particle, so in that case, Q is usually C times P squared. You replace Lagrange multipliers with ghosts, etc. Okay, but we know the answer, but we haven't gotten it from gauge fixing. So now the question is, how can we get this answer by starting with an action? Okay, so the naive thing to do, and this is something that Orm Siegel investigated, is just treating d alpha as a constraint and just adding Lagrange multiplier. Now this, of course, doesn't work because this has a second-class piece in it. So if it was just first-class constraints, that would be the obvious thing to do. And then you would get what you want. Okay, so what would you get in this case? Well, you get Q is equal to C times P and Pn plus. Now, as I just told you, this is not nilpotent because, so lambda tilde alpha is, the tilde means it's not constrained. Okay, so if F alpha was just an ordinary fermionic parameter, unconstrained, this, when you go to BRST, the ghost is just an unconstrained bosonic parameter. But because this is second class, this is not nilpotent. So I want to add something to it which makes it nilpotent. So the term we're going to add is this. Okay, so this tells you that not the lambda tildes are not all independent, they satisfy.
So there is no way to first project onto those d alphas which are first class and then add constraints like this, add Lagrange multipliers.
So remember the part which is first class is this P slash D.
Yeah.
So this would be consistent. This would give a nilpotent BRST operator, but now you still have the second class constraints that you can't just ignore. So this would give you a Hilbert, the phi's which was annihilated by these would have many too many states. So you need somehow to impose the second class. I'm going to write this. Okay, so what I'm doing, this part would come from here. And now I've kind of added these things by hand in such a way that the complete operator satisfies q squared equals 0. So if you take the commutative, it's not so straightforward to see, but I can tell you what C is. So C is the same C as we had before. Sorry, I used them. Which means I should add a term here. So I'm trying to construct something which plays the role of being halfway between the light cone gauge, Green-Schwarz description, and this pure spinor description that we're going to land on. So what I want to show is that with this type of BRST operator, I can either gauge fix to the light cone gauge Green-Schwarz, semi-light cone gauge, or a new formalism, which I'm going to call pure Spinor Formalism, which has the following degrees of freedom.
But earlier you didn't have to add them, right? Didn't they come from the action itself, the part of the theta dot gamma theta? No?
I'm sorry?
Why are you now adding xi comes?
Yeah, I didn't explain it right. Let me, so what I want to do, okay, so let me try to explain better.
This quadratic term in theta already has some side, right? That are kind of terms.
Yes, but if I construct it in this way, this d alpha, let me say it, let me say it more, let me say it in a way which is more consistent. That's the problem of looking at notes, which I wrote a long time ago. I want to the d alpha is not first class. Let me try to construct something which is first class. So let me call d tilde alpha to be d alpha plus p slash gamma plus c alpha squared to p plus. I think I'm doing this right. So let's compute where C satisfies this anti-commutation relation. And let's write this as dl due to tau. So why have I done this? What am I trying to do? I'm trying to land on this BRST operator by starting with a system that I know how to quantize. Now this system here is not Lorentz covariant, because obviously A is 1 to 8, and this D tilde is not Lorentz covariant. But if I did the computation correctly, this should satisfy the D tilde, with D tilde is proportional to P squared.
What is the A index here? C has an A index here, right? That is unconflicted.
A index is which? So this C, gamma plus C only chooses the A index, if that's what you're asking? What was the question?
The C has an A index, right? 1 to 8.
Yeah, so
That is A also.
you're right. Okay, let's do. I'm being sloppy with. Okay, let me. Okay, I think the most efficient way to do this is to leave this for tomorrow. Let me fix all the indices, and let me go to the next. Okay, sorry. Let me tell you the idea, and I'll do it tomorrow. So the idea is I'm going to put in a D tilde here, which is first class. And I will show that this action can be gauge fixed in two ways. One gauge fixing is to use this constraint here to gauge state equals 0. In that gauge, this term drops out, and we're back to the semi-light cone gauge Green-Schwarz. Okay? And in that gauge fixing, there's no BRST operator. The other gauge fixing will be not to gauge theta to 0, but to gauge lambda tilde to be equal to be a pure spinor, and to gauge psi to 0. In that gauge fixing, what happens is that this action is going to reduce to this. So I'll write it in two ways. One way is theta dot. Which can also be written actually there's no E. Okay, so this is the pure spinor action. To go from here to here is trivial. You just use the fact that d alpha is equal to p alpha plus small p alpha plus p slash state. If you write it this way, it's manifest as space-time supersymmetry, because this expression and this expression are both space-time supersymmetry. If you write it this way, it's obviously a free field action. Now, to get to this gauge fix, to get from here to here, you have to do a gauge fixing which yields ghosts, and Q is just going to land on this. So Q. Okay, so I'll do that tomorrow. The only warning I should give you is that the starting point is not manifested Lorentz covariant. So what this shows is that this action here with this BRST operator is equivalent to the Green-Schwarz and semi-light cone gauge. But the starting point is not manifested Lorentz covariant. So there's no nice way of starting from a Lorentz covariant gauge invariant action and landing on the pure spinor form. So that's something that one would like. I mean, in bosonic string theory, you start with Nembu-Goto, or the polar curve action, and you gauge fix and land on the action conformal gauge. In pure spinor formalism, the end point is very nice, but the beginning point is still not so nice. Okay, so tomorrow...
The end point is just this.
Yeah. So the end point is just, you have a free action.
I'm sorry, the factor goes from where? Against theta dot be, yeah.
Okay, so in this one you come, when you do the gauge fixing, this F alpha is going to transform under the gauge transformation like Lagrange multiplier with the derivative. I didn't say that right. Let me answer it tomorrow, because now I'm starting to confuse different things that I've done. So, you want to know where this term came from?
Yeah, that's it.
I'm sure there's a nice answer, I just don't know it right now. So let me put it tomorrow.
And the lambdas don't appear in the action.
Yes, they do, sorry. Thank you. So they come from the usual, that comes from the usual van der Popper procedure.
So W's are the
Nice
analog of E.
I'm sorry?
W's are analog of the E host, and lambdas are like C host.
Yes. So this term can be obtained.
I think that
This term can be obtained just by a shift of F. You just shift F by F plus theta dot.
okay.
Okay, I'll do this tomorrow. I promise to write it down. Okay, so the punchline is that the starting point is not so nice, but it allows you at least to show that this is equivalent to electron Green-Schwarz. Connecting to RNS, I have written some papers, but certainly nothing is very nice at all. So of course we can go from light cone Green-Schwarz to light cone RNS. So connecting this to light cone RNS is no more difficult than to light cone Green-Schwarz. But one would like to connect to covariant RNS without having to go through light cone gauge. And that seems to be harder than one would think. Now, the fact that it's hard may not be surprising, because we know that this is nice for GSO plus sector, whereas RNS is nice for Green-Schwarz sector. So there shouldn't be a nice way to go from both sectors to both sectors here, because the sectors are different. But in any case, this is maybe in the last lectures I'll discuss some open problems. Okay, so in any case, the action is simple. The BRST operator is simple. What I've shown already is that at ghost number 1, you get, so ghost is this lambda, and I'm going to define it at ghost number 1, so that the BRST operator has ghost number 1. And I've shown you that the cohomology of ghost number 1 is just superangular. Now, what about the other ghost numbers? No, this is, you can either treat it as an exercise, or you can think a little bit about how it works in bosonic string theory and see that you get the same type of answer. So let me remind you what happens in bosonic string theory. Okay, so in bosonic string theory, if you ask for states of conformal weight 0, so they describe the massless state, you have the object DC, C has conformal weight -1, so this has conformal weight 0. You have, of course, the identity. You can also write things like C DC times D squared C. And then you also have, okay, that's right. This has conformal weight -1. You can have vertex operators that have conformal weight +1. Now this has conformal weight, this has ghost number 1 and conformal weight 0, but if I'm not mistaken, it's BRC trivial.
Del C is not BRST invariant.
Say it again? It's not BRST in fact, even better. Okay, so it's not in the cohomology because of the BC DC term. Right. So Q, remember, in bosonic string theory, CT plus DC DC. Okay, so this one goes away. But what you do have is C DC times V. Okay, so these are the three types of cohomologies in bosonic string theory. You have the identity operator. You have states of ghost number 1, which is C times vertex operator conformal weight 1. Primaries, conformal primaries, dimension 1. This is the same V as before, but now instead of multiplying by C, multiply by C DC. And then finally you have the state C DC D squared C. So all the cohomology is at ghost number 0 to 3. And the state at ghost number 3 turns out to be the zero mode measure factor. So on a disk, integrating over the C0 modes is the same thing as just pulling out the term proportional to C DC D squared C. Now the structure of this BRST operator is analogous. So we have three types of four types. We have cohomology equals number 0. The only state is the identity operator. So just remember, we're looking at the cohomology of this operator. And at ghost number 0, in general you can have a function just of x and theta, but q on it equals 0, so lambda alpha d alpha equals 0. That has to be true for any lambda, so that implies that d alpha phi equals 0. Which implies that phi is constant. Okay, so it has to be proportional to the identity. It goes number 1, we already argued it was this. Now it goes number 2. You can have something which is a bispin.
You would say triangle primary, right? If D alpha phi is 0.
What, so d alpha phi equals 0. That because of the anti-commutator d alpha with d beta equals dm, that implies that dm and phi equals 0 also. So that implies that phi is constant. Okay, ghost number 2 is more interesting. So if you require the q on this object equals 0 up to BRST trivial, it turns out that this object describes the dual to superangles. What does the dual mean? So Carlos, you're not going to discuss this, I assume, is it?
No.
Okay. So what he will tell you is that A alpha, if you expand it out, it has a term at order theta, which is proportional to the gluon, and it has a term proportional at theta squared, which is proportional to the gluino. If I put the indices here, you'll get something like this. Now, if you expand A alpha beta out, when A alpha beta is in the cohomology of this, it turns out that it has a field which has the opposite chirality to the gluino. So So it's anti-chiral instead of chiral. And instead of sitting in order theta squared, it sits in order theta cubed. So I'm not going to try to write all the indices out unless people want to know. And then it has dual to AM, or A star M, at order theta the fourth. Okay, so I didn't write this. So this is some combinations of thetas which have these indices, and some combinations of theta the fourth which has these. And if people want, I can write down the indices. I'll tell you how I know how to write the indices later, but this is going to be the dual to this, and this is going to be the dual to this. In precisely the same way as in bosonic string theory, you can interpret this to be the dual to this. So why do I say this is the dual to this? It's because if I take the correlation function, this object, and use this measure factor, this just gives me VV star. Now, if you look at the counting here, you'll see that you'll get a similar term if the measure factor is proportional to theta the fifth. And that's exactly what you find. So in ghost number 3, you find this unique state.
So from the space-time perspective, should we think of these as antifields of the angle state?
Okay, so just 1 second. Okay, so why do we think of, okay, so let me say first why we think of these as the antifields to these. That would be an easier question to answer. Okay, so the states in cohomology goes number 2. If you look at the equations of motion, or more precisely, the gauge transformations of the states in ghost number 2 are related to the equations of motion, the states in ghost number 1. So let's just see how that works. So if I want to write down the gauge transformations, so if I define phi, so this, let's say phi is something of arbitrary ghost number. So phi has a term A of ghost number 1 plus now if I ask what's the gauge transformation of A2, if I define gauge transformation of phi to be the Q of lambda, then the gauge transformation of A2 is going to be related to the lambda at ghost number 1. So it's going to be something like lambda 1. If I similarly expand lambda in a similar fashion. So what do I want to say? So, okay, it depends what your favorite definition of antifield is, but so let's look at so let's do Yang-Mills. So the equation of motion for the gauge field is dm em an equals 0, and the gauge transformation is delta an is equal to dm lambda. Now the antifield, the equations of motion are, let's call it A star, delta of am star is equal to dm whereas the equation of motion is going to be, if I remember correctly, dm am star. So you see the equation of motion, the gauge transformation of the antifield is similar to the equation of motion for the field. And that naturally happens just because of this. So this, the way this A2 comes out is the same way as the equation of motion for A1 will come out, because of this, just from the different ghost number. Okay, now, I'm not sure if that's enough for you, is it? So the same property will happen here. If I write down the phi q phi action, let's see. So you probably can tell me more about this than I can tell you about it, but
but I will say if you just do BB quantization, right?
yes.
Then at least in string field theory you get all the antifields from the ghost number, right?
Yes.
And so the question is it the same here?
Yes.
Suppose you take the Albert's theory and do the BB quantization.
Yes.
Then these will be the antifields.
Yes. So, so what you find is that, okay, so these fields here, so, I mean, I think you answered the question you asked, but A star M, if you ask what is the cohomology of this, you find that at order to theta the fourth, there's a term A star M, which has the same cohomology as the dual to the cohomology of this and satisfies these equations here. And similarly, chi star would be the dual to the chi. Now, not surprisingly, you can define the action. So if I define phi this way, you can define the action to be okay, you can even write down the phi cubed. So in bosonic string field theory, using this measure factor, you can show that this gives you the usual BV form of the action. So the same can be done for superpositing Mills in the 10-dimensional case. But what one needs to explain in this, maybe I can do. So I should finish in 5 minutes, right?
I mean, we finish at natural stopping point.
Yeah, okay, so let me plan to finish in 5 minutes. So the idea is that this same type of action can be used for the pure spinors, where the measure factor is going to be this. Okay, so let me say in words what I'll start to do
Particle?
tomorrow.
It's an action for the particle in space-time.
That's right.
And
For superpositing Mills.
and you get this the q lambda alpha d alpha from that.
So I will use the Q that I'm defining here, and I'm going to plug it into an action of this type, where phi is now going to be a function not just of x and theta, but also of this lambda. And what I'll explain tomorrow is that this kind of, the funny thing is that I haven't explained it, I'll explain tomorrow, is where this factor comes from. So let me just say a few things in words and then I'll say what I'll do tomorrow. So this, I mean, even for the bosonic string, you have to do a little bit of work to show that these are the states in the cohomology. In this case, you have to do some more work, but you can prove that this one I think I already did for you. This one you have to do some work, okay? But the thing that takes even more work is showing that the cohomology finishes at ghost number 3. So lambda is a bosonic object, unlike C. So you might say, okay, this is not surprising because C has only 3 zero modes on a disk, so how could you possibly get more cohomology? Here, lambda is bosonic, so you can have arbitrary number of bosonic zero modes. But surprisingly, the ghost number finishes at 3. Okay, I don't think I'm going to prove that to you unless somebody wants a proof. But what I will say tomorrow is how to understand this measure factor here. So this is going to be crucial for what Carlos, for example, describes about computing tree amplitude. And it also will explain why this is the dual to this. Because if you look at the structure, this A, you see that the dual always involves 5 minus the thetas here. Okay, so it turns out there's a similar structure in 11 dimensions. That's a sign. In 11 dimensions, there's a similar structure, and there's, when you do the 11-dimensional superparticle, you'll get an expansion for the supergravity fields. They're similar. Instead of it goes number 1 and goes number 2, the relevant cohomology is it goes number 3 and goes number 4. So you can see that tomorrow. Okay, so I'll stop.
For supergravity, you have similar type of construction of the action also?
Only at linearized level. So Martin Sedwall has done beyond linearized level, but I don't understand it well enough to talk about it. At the linearized level, yes, this is correct. So this gives you the linearized supermembrane. The linearized supergravity actually.
And this construction goes through because of maximum specificity?
I wouldn't say it so strongly. It only works, I only know how to do it in the maximally supersymmetric case. I don't, as I already mentioned, the cohomology, Q is not, this cohomology is too weak in the case which is not maximally supersymmetric. So I can't say there's no way to fix it, I just don't know how to do it, and it's not maximally supersymmetric.
So for supergravity, it will be non-polynomial?
If you want to do the full theory.
Yeah.
Well, has done. So he has an action which is polynomial, but it has some extra auxiliary fields. And if you solve for those, you'll get the full non-polynomial action. But his action is just quadratic in the field. Is that right? It's quadratic, right?
For what theory?
It's quartic. I said quadratic.
For
Quartic for supergravity.
Yeah.
It's quartic, right?
It's quite different.
So it's quartic, but when you solve the auxiliary field, it should give you something non-polynomial.
And for young males, it's just Q.
For the 10-dimensional.
For 10 dimension.
Yes.
If you have non-abelian angles, I guess this is for abelian.
Yes, so, sorry, so for non-abelian, you just put in a trace, so the phi cube term is just, it's the usual. So I just put in the structure constant.
So you add like a Chan pattern, I mean that kind of.
If I'm doing the particle, I don't need to say Chan pattern, it's just, yes, the cubic term is anti-symmetrized with the structure constant.
And the quartic term comes from some auxiliary field elimination.
Yes. So in Super 8 mils, it's easy to see. So I think you already know this, but so you get, for example, FMN, of course, has a quartic term in it, but that just comes from. I can easily write it. If DMN is an auxiliary field, this is of course equivalent to this.
Any more questions? Yes. Thank you.